I'm not telling you how nothing from that one. Well, are you very I can't trust that. Like, actually, don't matter, bro.
Like, I'm not just politically involved,
But like, you care if you keep up to date with stuff.
I think it's very important that a citizen of a nation for the world is kept up to date.
That's good.
Are you referring to the situation in Canada or the situation in the United States?
The United States is like, they got their own thing that affects everybody else. I mean, that's true. But like, if you think about it, the United States is doing really well right now. That's because Trump is just like, guys, do your thing.
You're not serious, are you? There's a lot of people who have that opinion, and it's absolutely insane. It's insane to think that he knows anything about what the US ever.
I know. He's like mentally insane.
He's legitimately a not well individual, but he's the most powerful person on the planet. Okay, let's try this. I would like you to take out your 13.3 notes, please. What? Can we do a lab?
Instead of notes? That sounds like a great idea.
We're gonna do something very, very mentally intense today. That's our plan. You what?
I had a spare for you once, so I just left for a while.
So Max is good to go. Yeah. Okay, I would like you to turn to these practice problems. We're not really gonna do them, but we're gonna take a look at them and we're gonna try and see what's going on if we can identify some redox reactions. So let's take a look at A. When I look at that first reaction, somebody talked to me about a plan. How could I identify how could I say indicate whether the equation represents a redox reaction? So how can you tell if something is a redox reaction, Matt? If the oxidation numbers of any element changes at all, right? So let's take a look at copper. What's the oxidation number for copper? 0. So let's take a look at copper again in the other side of the equation. After it's done reacting, what's the oxidation number for copper? 2. Not 0. That's really all you need to know, right? But let's think about this. Let's try and make sure we actually understand what's going on. Copper is attached to a nitrate or two nitrates. What's the charge on one nitrate? -1, right? There's two -1s, so that means the copper has to be +2. Did it change? Yes, so this is a redox reaction. Absolutely, this is a redox reaction. Let's take a look at B, and really quickly, let's try and identify the lead. What's the charge on the lead?
2.
It's +2, right? So that's 2 plus +2. That means its oxidation number is +2. Let's look at the lead over here. What's the charge on the lead over here?
2.
That's +2 as well. That's a really good indication that this is not a redox reaction. So far. We could go through everything in here. Does the nitrate change? No. So let's just cross it off because we don't really care about it. Now we just have to look at potassium and iodide. What's the charge on the potassium here? What's the charge on any potassium ion ever? +1. So it's +1, and the iodide is -1, just because that's what an iodide ion is. And then, okay, well the iodide, yeah, that's -1, and the potassium is still +1. Did any of those numbers change? No, that's not a redox reaction. Let's take a look at C. What element do you want to talk about first? Chlorine, potassium, or iodine? Iodine. Sure, let's talk about iodine. So let's take a look at iodine. In potassium iodide, The potassium is +1. The iodine has to be -1. Are we okay with that? It's like a regular ionic compound. Thank you. And what's the oxidation number for iodine here? 0. So did it change? Yes. Yes. Do you know what I mean? Like, it doesn't have to be a really, really intense, long problem. All you have to do is just look through and look at the metal first, maybe, or just identify one element and see if it changes. I want you to do the next 3 for me and tell me if they are or are not redox reactions. I'm going to give you a minute to do that. Yep.
Yeah, I did a little bit of G. So.
But we did G together yesterday. Yeah. But anyways, you can do it again if you want.
No.
I'll give you 10 seconds just to finish up the equation that you're working on. Okay, let's look at D. Let's look at it together. The sodium and the sodium, did the oxidation number change? Yes. The sodium here is +1, the sodium here is 0. So yeah, that's a redox reaction. Absolutely. What about everything in here? No. Okay? And so we ask ourselves, does the OH change? Not really. The OH combines with the H to make H2O, so the hydroxide didn't really change, right? The hydrogen's still kind of +1, the sodium's still +1, the chlorine's still -1. So that's not a redox reaction. The aluminum goes from 0 to +3. Immediately, yeah, that's a redox reaction. Yeah, totally. Any questions about that? Nope. Seeing none. Okay, we're going to move on to one of the most important ideas in this unit. Now, oxidation numbers are the foundation of a lot of things that we're going to be doing. We still have to use oxidation numbers here. But what we want to do is we want to balance a reaction. And balancing, does anybody in here think that they're pretty good at balancing reactions?
No. Yeah.
There's a few people, right? Let's take a look at this. Is this reaction balanced? No. What's one glaring problem that you see with this reaction?
What happened to the oxide?
Okay, so there's absolutely no oxygens in the second half, not second half, but in the products at all. There's no oxygens at all. Could you balance this using the normal skills that you have? No, if there's no oxygens here, you can't put a number in front of nothing. So we have absolutely no clue what we have going on here. One thing I want to say, you will always be balancing these redox reactions in something that we call acidic solutions. And so this reaction is happening inside an acidic solution. So we've got a couple extra pieces of information that we could add at any point in time if we wanted to. What makes an acidic solution? What are 2 things that you need in order to make an acidic solution? Jordy, give me one. You need hydronium. Again, we're going to call it, we're going to think of it really, really basically, but we're going to call it, cross out basic solution. We're not going to do any basic solutions. Something that makes something acidic, hydronium, or even more simply, is H plus. Okay? Because really, something that's acidic is just a proton hopping from one thing to the other, right? So we just want to think about it that way. And then what's something else that we have in an acidic solution, Macy? Water. We have water. So we have water at our disposal. What's the formula for water? H2O, and that's where the oxygen's going to come from for us to be able to balance this. We're going to add oxygen in the form of H2O on one of the sides of this reaction. But we've got to do some things first, right? So it's acidic, and then it's a solution. So that means we have H2O at our disposal. At any point in time, and it's going to be one of the last things we do, but at any point in time, we could always add H plus to one side, or we could add water to one side. Okay, example, balance the following reaction in an acidic solution. So step 1, we want to assign oxidation numbers and identify the atoms or ions whose oxidation numbers change. So let's go through here. What do you want to, start at a specific point, or do you just want to look for the easiest stuff? Let's just do things that are the easiest first. What's something that's really easy in here? All of these things by themselves, right? Okay. So what's Cl minus? What's the oxidation state for that?
0.
So is this an element all by itself with no charge? It's an ion. It's not an element. This would be an element. So what's the oxidation state of this thing? 0. Okay, what's the oxidation state of Cr3 plus? 3 plus, or plus 3. I should say plus 3. Whoops. Okay, now it's that one that we got to figure out. Oh man, isn't this one of those complicated ones that we got to figure out? No? What's oxygen gonna be? Okay, -2. And so let's try and set this up. Off to the side, or somewhere on your neighbor's forehead or whatever. You can do the math if you want to. We need 2 CRs, and there's 7 oxygens, right? So 7 -2s. And what does the whole thing have to equal? It has to equal -2. Okay, let's think about this. That's -14. And we want to balance 12 of the -14s because 2 have to be left over. So if we want to balance 12 or cancel out 12, what do each chromium have to be? +6. Okay, now I'm going to erase that. So it doesn't matter how you get it as long as you get it. That's all that matters to me. Matthew. Good job.
He's just really happy about this.
Yeah. Okay, let's try this. We assigned oxidation numbers and we identified atoms or ions whose oxidation numbers change. So what changes in here? What's changing in this reaction? CR is changing. Is it gaining electrons or is it losing electrons? It's gaining negatives, right? So what are we going to draw? A squiggly arrow up. Referring to electrons are combining with the chromium to turn into chromium 3+. Now what's losing electrons? Cl minus is losing electrons. Okay. So that was step 1. We just had to identify which things are gaining and which things are losing. Step 2 is using the change on the oxidation number, write the number of electrons transferred per atom. That's where the PA in PAFU comes from. So we're going to be doing something called PAFU, and that's what we're talking about right now, okay? So per atom, the chromium starts at +6 and it ends up at +3. So per chromium, how many electrons were gained? Yeah, so we wouldn't say -3, we're just saying 3 electrons were gained. So let's write that, 3 electrons per atom. What about the chlorine? What's the difference in these oxidation states? Just one. And it doesn't matter that we're gaining or losing. We know we're losing. We've already identified that. So 1 electron per atom. Now the next part is where people get freaked out. So sure, per atom, this is what happens. But how many chromiums are in the formula unit for this whole thing, for this dichromate ion? There's 2 of them. Each of them has a change of 3 electrons, right? So if there's 2 of them, what's the total change in electrons in the whole formula unit?
6.
It's 6. So we want to write 6 electrons in the formula unit. Does that make sense? So we're analyzing per atom, and if there's multiple of them, then we have to change it to be in the formula unit. How many electrons are being transferred in this formula unit? Well, just 1, because there's 1 of those things, right? So the number's not going to change at all. Does that make sense? In the formula unit, if each chromium accepts 3 electrons, and there's 2 of them, we'll say 2 times 3 is 6 electrons. So the one chromium accepts 3, the other chromium accepts 3, so in the whole thing, it accepts 6. In here, there's only 1 chloride, so the formula unit is the same thing as per atom. It's the exact same thing. There's only 1 of them. Okay, no problem. Any problems with that? I said no problem, and I said any problems. All right, whatever. Now we have to calculate the simplest whole number coefficient for the reactants that will balance the total number of electrons transferred. Basically, what we're looking for is we're looking for the lowest common multiple of electrons. What's the lowest common multiple of electrons between 6 and 1? What I want to ask you is that if I wanted to make groups out of 6 and groups out of 1, we want to know how many of each would we need. So let's think about this. If this thing is gaining 6 electrons, where's it getting its electrons from? Who's losing electrons? The other one, the chloride. But this thing only loses 1 electron. We can't lose 1 electron but then gain 6 electrons. That doesn't make sense. If we gain 6 electrons, we have to lose 6 electrons. So how can we change this equation so that we can lose 6 electrons here? We're going to toss a 6 in front of there. But first we have to identify the lowest common multiple between 1 and 6 is 6, right? We can only make groups of 6 here, and this can make groups of 6 if we have 6 of them. So it's important that we identify every single time the lowest common multiple will be 6 moles of electrons. In this reaction, we will have 6 moles of electrons being transferred from one thing to the other. So let's change that. Let's alter our equation now. So do I have to put any numbers in front of the dichromate? Do I have to put any numbers here, or am I good with just 6 electrons? You're chilling, you're good. Yeah, thank you, Denver. Cr2O7, 2 minus, aqueous, plus how many chlorides do I need? 6. So 6 chlorides. Would you agree now that we're losing we're losing 6 electrons here and we're gaining 6 electrons there, so that's fine. The electrons, the amount we've lost and the amount we've gained is okay now. Okay, now let's balance every element that's not oxygen and hydrogen. Let's balance every element that's not oxygen and hydrogen. What was the first product here? Chromium 3+. So let's balance chromium 3+. How many, because I changed some numbers over here, how many chromium 3+s should be here now? there's 2 chromiums in dichromate, so I need 2 chromium 3 pluses. If I go back, we're also making chlorine. How many chlorines do I have to make? I have to make 3 because I have 6 chlorides, and 3 times 2 is 6. So would you agree every element is balanced except for oxygen and except for hydrogen? Yeah, perfect. Now we're going to balance the hydrogen or the oxygen atoms by adding water to one of the sides. And then once we've done that, balance the hydrogen atoms by adding H+. So it doesn't matter what side we add it to, we have to choose the correct side based on what's going on. Where do you want to add the water? Do you want to add the water to the left side or the right side? Why do you want to add the water to the right side? Because there's 7 oxygens over here and we need 7 oxygens over here. So that's what I'm going to do. You can continue balancing this if you want, that top reaction, but I just have to write it over again because I'm starting to run out of room. So Cr2O7 2 minus plus 6 Cl minus gives us 2 Cr3 pluses plus 3 Cl2s plus how many waters do I need? 7 H2O liquids. So would you agree our oxygens are balanced now? Yep. So now what's the only other element that we need to balance? We want to balance our hydrogens. Where am I going to put my hydrogens? I got to put it on the left side. Most of the time I have to put it on the opposite side from the water. So how many hydrogens in total on the right-hand side? 14. So I have to add 14 hydrogen ions to this reaction. Wow. How do you know that you've made an appropriate reaction? How do you know if you are perfect right now? If you're feeling really good about it. Well, that's your intuition, right? That's your gut feeling. Okay. Anything else? Jordy?
You're balanced.
If you're balanced. Well,
And charged.
oh, there we go. So we just balanced it using the conservation of mass, didn't we? We balanced it. If I've got 6 hydrogens over here, I need 6 hydrogens over there. It wasn't 6, but you know what I mean. So the only other way to know if your equation is balanced is by using the law of conservation of charge. Let's add up all of the charges on the left-hand side, and let's see if they equal all of the charges on the right-hand side. This is going to suck for some people, but that's fine. What's all of the charges on the left-hand side balanced? Or added up to these? 14 minus 2 minus 6. Right? Positive 14 minus 2 minus 6. What's that up to be? That's positive 6. And what is the entire right-hand side? That's positive 6. I've got 2 groups of 3 plus, so that's positive 6. Are we balanced? Yeah, we're balanced, totally. Now that's a complicated process. Let's just review what we did. I have to split it up between 2 slides, but it's all on one sheet of paper for you. What did we start off at? How did we start off? So we had to figure out what was gaining and what was losing electrons, right? And the way we do that is by assigning oxidation numbers. Then we had to do PA and FU. If you don't do PA, FU, you're sure going to get F'd up when you do your diploma. So that's why we do it, okay? So you're going to do PA, FU to figure out your lowest common multiple of electrons. Lowest common multiple between 1 and 6 is 6. So we're just going to do 6. What if it was 2 and 5? What's the lowest common multiple between 2 and 5? 1. If you wanted to make groups out of 2s and 5s, but you wanted them to all add up to be the same, the lowest multiple you can make is 10, right? 2 groups of 5 and 5 groups of 2. Alicia. So I want to make this thing gain a certain amount of electrons, and I will what?
The charge. At the bottom.
Here?
Yeah, how'd you get 6?
How did I get this 6?
No.
How did I get that 6?
Yeah.
I have 2 groups of positive 3. So if I have 2 times positive 3 is positive 6.
Yeah, but on the other side, you added up the 14 and 2 and 6.
Yep.
And then you added 2, the 3, and 7.
There's no other charges over here. I'm just adding up all the charges. So there's 0 charges here. There's 0 charges here. And so these are the only charges I have to pay attention to. Is that okay? Yeah, no, that's a good question. Okay, let's try another example. Is that okay? Yeah, but you have the list of instructions. Now, you shouldn't need 1 page of room to do this because all we really did was draw some squiggly lines and then we balanced it, right? That's all we did. So let's try this. What's the first thing we need to do again? We have to figure out what gains and loses electrons, and we do that by assigning oxidation values. Oh, is it not attached to your notes package? Sometimes the printer likes to play tricks on us. Is it this single page right here? Sorry about that.
How did you get +4 from SO?
Can we talk about it?
Yeah.
Yeah. I'm going to give people like 10 seconds to finish doing the oxidation states. Okay, let's go through the oxidation states of this reaction and let's see where I got some of my numbers from so far. Are we good with the +3? Yeah. Are we good with the 0? It's everything else that gets complicated, right? So why did I put a -2 above the oxygen? Because when it's in a compound with something else, we're just going to give it -2, right, most of the time. So if the whole thing has to add up to be 0, I've got 2 -2's, which is -4, and there's only one S, so it has to be +4 to cancel out all of that -4, right? The whole thing has to add up to be 0, so that's where I got that from. What about the SO4 and the sulfate? What's the oxygen? -2. And so what does the sulfur have to be in the sulfate? It would be, if it was neutral, it would be +8, right? But it's not neutral. This has to cancel out all of that negative except for 2 of them, so it has to be +6. For a lot of people, assigning oxidation numbers is going to be the hardest part about these problems. If I'm being honest, assigning oxidation numbers is going to be the hardest part. That's why we tried to do so much practice yesterday. Okay, what's gaining and what's losing electrons? The gold, is it losing or gaining?
Gaining.
It's becoming more negative, so it's gaining. And the sulfur, is it becoming more negative or more positive? More positive, so it's losing. Now, yeah, Jordy.
You just take the sulfur into account?
I just take the sulfur into account.
Okay.
Because is the oxygen changing? No. But the sulfur inside the sulfate, or the sulfur inside the SO2, I should say, it's changing. It's the thing that's changing, right? But we say the whole entity is gaining electrons, really, right? The whole formula unit, but it's the sulfur specifically inside of it. So what's the difference between the golds? How many electrons is gold gaining? 3 electrons per atom. And are there multiple atoms in here? No, there are not. So we don't change it. We just say 3 electrons in the formula unit. What about sulfur? How many is sulfur gaining? Or losing, sorry. 2 electrons. Where did we get that 2 electrons from? How do we know it's... So it's the difference between 4 and 6, right? In order to go from 4 to 6, you had to lose 2 electrons. How many sulfurs are in SO2? Just 1. So there's only 1 of them, so it's still 2 electrons in the formula unit. So what is, off to the side here, let's say what is the lowest common multiple of electrons between 2 and 3? 6. If you wanted to make groups, how could you make equal groups out of 2s and 3s? 6. So 6 moles of electrons. So how can I make, the gold is gaining 3 electrons in the formula unit. How can I make it so that it's gaining 6 electrons? We're going to put a 2 in front of it, right? So let's put a 2 in front of the gold. And we're going to put a what in front of the SO2? We're going to put a 3 in front of the SO2. Now that we've adjusted, would you agree that if I have 2 golds, they're now gaining 6 electrons? And would you agree that if I have 3 SO2s, they're now all losing 6 electrons? So now that we're losing the same amount as we gain, then we can balance this kind of the way we normally would. If I have 2 golds, how many golds over here do I need? 2. If I have 3 SO2s, how many SO4s do I need? If I have 3 sulfurs, how many sulfurs? 3 sulfurs.
But the oxygen stuff. Oh wait, never mind. I get it.
Yeah, because we can always change the oxygens later, right? Yeah. Plus 2 gold. Where do you want... Sorry, we balanced our golds and we balanced our sulfurs. So we did all the non-oxygen hydrogen elements. What do we want to do first? Do you want to do oxygens first or hydrogens first?
Oxygen.
You have to do oxygens first. Because when I balance with water, I change the number of hydrogens by default by adding water. Where do you want to add water to? Left side or right side? Over here. 6. How many oxygens over here? 12. 6 over here and 12 over here. So I need to add 6 waters to this side. Because I've added 6 waters to this side, what do I have to add to the opposite side?
12.
I need to add 12. And that's only because there's no other hydrogens, right? So I need 12 hydrogen ions. Look. I wish my smartboard was wider, then I could write bigger, but I can't, so I won't. Yeah, George.
Can you go over again how, like, why the water on the left side and hydrogen on the right side? Like why you can't go?
Right now, all of our non-hydrogen and non-oxygen elements are balanced. Would you agree? Like gold and sulfur, they're balanced.
Yeah.
So what's the only other element that's left over? Oxygen. So we have to find out, where do we have less oxygens? Where do we have a deficiency in oxygens? Right now I see 12 oxygens over here and 6 oxygens over here. And so I should put more oxygens on the left side. What's a substance, Jordy, that has oxygen that's available to us?
Oh,
Water. So I will add 6 H2Os to this side. Again, because we're always balancing in an acidic solution, we always have hydrogen ions and water available for the reaction. So here, we're using up a little bit of water. Then, once we're done balancing oxygens, it's just hydrogens. Where's the only place you see hydrogens anywhere in here? In the waters. So if I have 12 on this side, I have to add 12 on this side. What's our check? How do we double check that we made appropriate decisions?
Charges.
You have to add up all the charges. Go ahead and add up all the charges. One side is always easier than the other. Are we good? Yeah, you can. We've got a total. Okay, do the waters have any charge?
No.
No, and I've got positive 6 from the golds. Do the SO2s have any charge? No, so I've got a total of plus 6 here. Over here, there's 2 things with charges. I've got a total of plus 12 over here and a total of minus 6 over here. So what does that have to be? Positive 6. So positive 6 and positive 6, we're good to go. Any questions about that? Now, these questions, these examples are really not that bad, the solving this. It's understanding what am I supposed to do first, right? So when we look at this next example, it says balance the following reaction in water. It should say an acidic solution, but whatever, that's all good. How do you balance a redox reaction in an acidic solution?
Oxidation numbers, GAF.
You have to figure out who's gaining and who's losing electrons. So you do oxidation numbers and PAFU. I want you to try this out, and I'm going to walk around, and then I'm going to show you whether or not you're right. Yeah. So there's 5 electrons per bromine. Yep. How many bromines? Just 1. So it's the same number. There's only 1 atom, and the formula you need is Where did you get 6 from?
-2 plus 6 is 4.
Is the carbon -2? Yeah. In order for everything to add up to 0, the carbon has to be -2. Yeah. So when you go from -2 to 4, that's 6. Let me know if you're stuck on a problem, even if it's on the first step. Let me know, and I can maybe help you out. Let's add up everything so far. Okay, so you've got 6 positives and 2 negatives. So that's positive 4. So we need to cancel out the positive negative. So this whole thing, C2 needs to be -4, right? But what's H2?
This can't be -2. -4.
So how many? Because this is per atom. So when we're talking about per atom, which atom are we talking about? The entire thing? We're talking about like BR. So like this is right. Wait, so no, we're finding the difference. Look, the difference here. See, this goes up by 6. This goes up by 6, so it would be 6 even 12. The common difference here is 12, so this would be 1 less right here. So have a 2. So you compare this to this. Oh, okay.
We're just looking for this.
Compare this to
So if I have 1 carbon, it would use 6 electrons. If I have 2, that's
here, there's got to be 2 on the other side, right? Okay, so there's 6.
well, it's whatever.
So there's 6, 7.
If I just
This is 2, 6.
so how many electrons?
There's 8.
If I took minus 2,
Yeah.
or if I took 2, you get 6. Yeah.
Oh, it's for.
Well, unless it's totally right? Yeah.
Like,
So what's the everything else?
It's because I was like,
it wasn't called, because you know.
I noticed that. Because it's also, we're also. So is this?
Why would you?
And then what's the carbon? Are you sure? No. Well, I don't know about more, yeah, about 16. So. 6. I don't know if it's anything yet. So it's just that. Once you get certain electrons in it, so is this thing?
These guys are 60. Actually made it. You guys go 6 times 12? This is 5. That's 7. So you have 2 rates of 5.
Plus 5, 6 is 12. If I want to go.
So look, there's 7 on this side.
I can't.
There's 7. There's 2 on this side, so it needs to be 5. You guys want to do 5 on this side. You're right, actually, you're right.
So I can't do any less than 12. So literally I can get.
That means this one's, there'd be 4. Whereas on this side, we're looking at, yeah.
You call me over here. But anything, bro. Sure. Okay, we're gonna talk about this together. Yeah, we're gonna talk about this together. Okay, so listen up. Don't get distracted by your best friend. It doesn't matter that they're your best friend. You shouldn't be sitting by your best friend. There it is. Don't worry about it. You say you're my best friend? No. I am your best friend, actually. Totally, I'm your best friend.
When's his birthday?
I don't know. I have access to it, but I don't know.
That's cheating.
Yeah, that is cheating.
I don't think that's
What's Jordy's birthday?
I don't know.
Don't lie.
Yeah.
That's private information. You guys
Yeah, that's right. I can't tell you. I don't know. You can tell them, but I can't.
Well, you already know.
It's actually, I don't even know.
You don't even know. Okay.
To be honest.
Are we okay with what I've written down so far? That's the basics of what I've written down, and that's just rules like 3 and 4. That's rules 3 and 4 on our oxidation numbers. Now, there's something else really, really easy to identify in here. What else is really, really easy? The Br minus, right? What's that? That's -1. Okay, now it's just a little bit of math. And what I would suggest to you is if you're having trouble with this, then write it out. Don't worry about it in your head. Write it out. So let's write it out. For the bromate, for BrO3 minus, what does the whole thing have to add up to be? -1. And there are 3 -2s, so that's -6. What does the bromine have to be? The bromine has to be +5, right? In order to cancel out 5 of those 6 negatives. So this has to be +5. Now let's do this one. This one's complicated, so please listen up. If you personally ask me how to do this, then you should definitely be paying attention. What does the whole thing add up to be? 0. And I've got how many oxygens? 1, so that's a -2. How many hydrogens? 6, so that's a +6. And I've got 2 carbons. Okay, what's +6 and -2 when you add them up? +4. So if those 2 carbons have to cancel out the +4, what do they have to be? So if I move the 4 over, it becomes negative, divide by 2, C is -2. So now, sorry, my lamp is dimming here.
Wake up lamp.
Wake up lamp, okay. So let's see. In here, do you see anything becoming more negative? What's becoming more negative? The bromine is becoming more negative, right? Sorry, we forgot the carbon and carbon dioxide. It's +4, right? So the bromine is becoming more negative. That means what? Is it gaining or is it losing electrons? If you gain a negative, you become more negative, right? It's gaining. So by default, if this is gaining, this has to be losing. So first of all, the first thing I want to ask you, what's being oxidized and what's being reduced?
Bromine oxide is being reduced.
So the bromate is gaining electrons, so it's being reduced, right? Grr. And then the C2H6O is losing, so it's being oxidized. Okay, no problem. So 5 to -1, what's the difference between +5 and -1? That's 6. 6 electrons Pa. So per bromine is 6 electrons. How many bromines do you have in here? You have 1, so the number's not going to change, right? If each bromine changes by 6 and there's only 1 there, then you change by 6. What about the carbons? What's the difference between -2 and +4? That's 6 as well. It doesn't matter if it's +6 or -6, because you've already told me if it's gaining or losing. So 6 electrons per atom. How many carbon atoms are in here? 2. So 2 times 6 is 12 electrons. Fu. All right, so let's try this.
I don't understand where you're getting these formula units from.
The formula unit is here. That is the formula unit for C2H6O. And so if one carbon changes by 6 electrons, how many carbons are in here? How many carbons are in here right now in the formula? 2 of them. So if one carbon is 6, 2 carbons will be 12. We're just multiplying this number and the 6th. That's all we're doing.
Ah, okay.
Yeah. So what's the lowest common multiple between 6 and 12? If you wanted to build the same number out of 6s and 12s, what's the lowest number you can build? 12. The lowest common multiple of electrons is 12 moles of electrons. So how do I get 12 moles of electrons? How can I get 12 moles of electrons out of bromate? I'm going to put 2 of these. So let's do that. Two BrO3 minuses. How can I get 12 out of the C2H6Os? You already have it. So what number am I going to toss in front?
1.
A 1, so we don't write anything. C2H6O aqueous. Okay, now that I've got my lowest common multiple, I'm gaining 12 here and I'm losing 12 here, right? If something loses 12, something has to gain 12 electrons. So how many carbons should I have here? 2, because I'm just balancing like normal now. 2 CO2 gases. How many bromides should I have over here? 2 bromines means I should have 2 bromides. So what are the only 2 elements that I need to balance out? Oxygen and hydrogen. What are you going to do first?
Water on the right.
You're going to do waters, and where are you going to put it, on the right or the left? Now, I don't have room. I see how many oxygens are over here? 6 plus 1 is 7, so I've got 7 oxygens over here. How many oxygens are over here? 4 oxygens. So how many more oxygens do I need? So I'm going to add 3 waters. So now what else do I have to do? What other element do I have to balance out? Hydrogen. I've got 6 and 6. I'm done.
Good.
Are we okay with that?
Yeah.
Are you sure that we got the right answer?
Yes.
How could you be sure? Let's look at our, let's look at our charges. How many charges do I have on the left-hand side?
-2.
-2 and 0 is -2. How many charges do I have on the right-hand side? -2. I'm good. So this is my answer here. It's the worst box in the world, but that's fine. Any questions about that? You don't like PAFU.
You just need to find the
It likes you, so that sucks.
You just have to find the difference of electrons.
You're finding what's gaining and what's losing, and you're finding the difference in oxidation states. That'll give you the electrons per atom
We multiply that
by the number of how many there are in that formula unit.
I think with more practice, I'll get it. But it's
Yes. I think with more practice, you'll get it too. I think with more practice, you'll get it as well.
Should we do it?
What do you mean, should we do it? Yes, you're doing this.
I would expected to.
What? Yeah, no, not as a class. You're individually doing this. I'm going to put this up on the smartboard, okay? So, but I might only be able to do question 12 at first. I don't know where they are on the page. So page 593. May I go run an errand that might rhyme with fetch my Lex book? Yes. Yeah. Oh, man. Page 593.
That's where my entertainment has come from.
Look at that. Oh my goodness. Look at that.
Whoa. Wait, that one says in basic solution.
Oh, which one?
13.
Oh yeah, just do 12.
Perfect.
It's all
Is it different?
Yes, it's for basic.
I know, but.
Yeah, just do 12.
Getting the hydroxide?
Yeah, so in the program of studies for the Alberta curriculum, it only says you need to know how to balance solutions balance acidic redox.
So are you 100% sure that it will not show up on
Yeah,
the
it's in your program of studies, which is the curriculum document that's
Yeah.
published for teachers to know. We basically have to memorize the entire program of studies, and in there it says that you do not have to know how to balance basic solutions, only acidic solutions.
Okay.
Yeah. So, no, I'm not going to show you how, because I don't want to waste your time. So, just do number 12. There's 3 questions on here. We already did A? Okay, then do B and C. All right.
We actually already did C too.
You're
Yeah,
just making
right.
this easier and easier for
Yeah.
Or you asked. Can I just do one instead?
No, do B and C. Just do B and C. Just do B and C.